and also connecting a 12-volt power supply. I have set up this LED arrangement to demonstrate the relays on and off functions clearly. This is a simple switch with battery connections. LED is connected to the relay. Now, when you press the remote, it should work, but it's not working. Upon future investigation, I found that this relay module has four selection modes. If any mode is not selected, the remote would not work. The small switch on the relay module selects between three modes. First mode, when I'm pressing the switch once, it called momentary mode. Then pressing a button on remote. After that, when I press this button on remote, relay turned on and by releasing turned off. The second mode is toggle mode. To use this mode, you need to press the small switch twist and then press either switch A or B on the remote. In my case, I pressed A. Now pressing A once turns the relay on and pressing it again turns it off. The third mode is the latch mode. To select this mode, you have to press the switch three times and then select A and B on the remote. Now pressing A once turns the relay on and pressing B turns it off. Besides these three modes, this small module can also function as a delay timer. When pressed 4 times, the relay will automatically turn off after a 5-second delay. Pressing it 5 times sets a 10-second delay and so on. Moreover, if you hold the switch for 5 seconds, you can reset the relay module. We can use two modes simultaneously. Here, switch A is set to momentary mode and switch B is set to toggle mode. The range of this module is excellent. I have tested it from about 50 to 60 feet without any issue. I hope I have provided some essential information about this relay module. Thank you for watching the video and stay tuned for more content. RF relay but it's not working. Upon future investigation, I found that this relay module has four selection modes. If any mode is not selected, the remote would not work. The small switch on the relay module selects between three modes. First mode, when I pressing the switch once, it called momentary mode. Then pressing a button on remote. After that, when I press this button on remote, relay turned on and by releasing turned off. The second mode. In this video, I will demonstrate a single channel RF relay module. It can be used for various purposes such as remote control door lock, home automation, and other tasks requiring remote control from a distance. This module operates on DC 12 volts, but it can control both AC and DC appliances. I will discuss also about some problems with it. This is its remote control unit. It feels quality good when you hold it in your hand. You need to insert a coin cell battery by removing those three screws, and then it will be ready to use, and it has an LED indicator. The relay module comes in an attractive box and also be mounted using screw if required. Here are some holes for wires. This is a 12 volt 10 ampere relay, a RF module with some other components. I am connecting the power supply input points with two wires and also connecting a 12 volt power supply. I have set up this LED arrangement to demonstrate the relays on and off functions clearly. This is a simple switch with battery connections. LED is connected to the relay. Now, when you press the remote, it should work, but it's not working. Upon future investigation, I found that this relay module has four selection modes. If any mode is not selected, the remote would not work. The small switch on the relay module selects between three modes. First mode, when I pressing the switch once, it called momentary mode. Then pressing a button on remote. After that, when I press this button on remote, relay turned on and by releasing turned off. The second mode is toggle mode. To use this mode, you need to press the small switch twist and then press either switch A or B on the remote. In my case, I pressed A. Now pressing A once turns the relay on and pressing it again turns it off. The third mode is the latch mode. To select this mode, you have to press the switch 3 times and then select A and B on the remote. Now pressing A once turns the relay on and pressing B turns it off. Beside these three modes, this small module can also function as a delay timer. When pressed 4 times, the relay will automatically turn off after a 5-second delay. Pressing it 5 times sets a 10-second delay and so on. Moreover, if you hold the switch for 5 seconds, you can reset the relay module. We can use two modes simultaneously. Here, switch A is set to momentary mode and switch B is set to toggle mode. The range of this module is excellent. I have tested it from about 50 to 60 feet without any issue. I hope I have provided some essential information about this relay module. Thank you for watching the video and stay tuned for more content.
A few years ago, we made a video about a 12V remote controller. It was liked by many people and is still watched by many people. At the same time, we also found many questions from the audience's comments. Now we have reorganized it, mainly to answer the audience's doubts on the original video. The doubts are as follows. Where is the power supply part? How to wire it? Explain the idea of wiring. Let everyone use this controller better. This is a 12 volts 433 MHz RF remote controller. There are two types of shells. The shell has corresponding openings. It is convenient for the wiring connection of the controller. There are also many types of remote controls. You can choose to match it as you like. Compatible with EV1527 remote control with a frequency of 433 MHz. We measured the specific range of the power supply voltage, which is 10 volts to 14 volts. We find the positive and negative poles of the power supply marked on the back. Here we use a lithium battery. The lithium battery is marked with 11.1 volts. It is the range of voltage that can be used. Connect to our power supply. This is the wiring of the power supply part. The LED light. It will light up when it is connected to the power supply. We lead out a line. Once these two lines are connected, the light will light up. The 12 volts remote controller is like our hands. It controls the connection and disconnection of these two lines. Take out the controller. Let's talk about what the following three symbols mean. COM represents the common terminal of the relay. NO represents the normally open terminal of the relay. When the relay is not working, the NO port is disconnected from the COM port. NC represents the normally closed terminal of the relay. When the relay is not working, the NC port is closed to the COM port. We connect it. Let everyone see the phenomenon more clearly. Our control logic is, when the relay works, the light turns on. When the relay does not work, the light goes out. So we have to connect this normally open terminal. You can also choose according to the actual situation. The best one is the one that suits you. Finally, we connect the power supply. The wiring is completed. This is a wiring method for external power supply. This wiring method does not stipulate the power supply of the connected device. It just controls the switch of the circuit. I will introduce the wiring method of shared power supply to you later. The power requirement for the connected device is also in the range of 10 volts, 14 volts. After connecting the wires, we start pairing the remote controller and the selection of pairing mode. The following is a detailed explanation. Let's restore the factory settings first. Press the learning button 8 times to clear all the previously paired remote controllers. Below I will show the effects from pressing 1 to pressing 7 times. Later, you can freely choose the required pairing mode according to the actual situation. All pairing modes are for different usage scenarios. For example, interlock mode. For one-button control of multiple controllers to turn on and off at the same time. Need to pay attention. If you press the learning button 8 times, all the previously paired remote controllers need to be repaired. This is a 12 volts controller with power connected. Take out a 12 volts LED lamp. Connect the LED lamp to the power supply of the controller. The LED lamp is also on. Next, we need to borrow this power supply. Then build 2 wires for on and off. We first connect the 2 negative poles. Directly control the positive pole. As long as the positive pole of LED lamp is connected to the positive pole of the power supply, the light will turn on. Let this part be handed over to the relay. Let the remote control the relay to help us control. Connect the positive pole of the LED lamp to the common end of the relay. Let a wire from the positive pole of the power supply. Connect it to the normally open end of the relay. Then when the relay works, the 2 wires are connected. The LED lamp is also on. Complete our goal. This is the wiring principle of the shared power supply. This is the wiring diagram. You can read it several times to deepen your understanding. At this point, you have fully mastered all the uses of this.
You're watching Keystone Science, and in today's episode, we're going to show you how to build your very own EMP generator. Okay, so some quick disclaimers before we get started. Devices that generate electromagnetic pulses such as these may not be technically legal to use in your area. I'm not sure where you are, so be sure you know the laws and to know what you're doing. Also, never use this on anyone else's devices or to cause destruction, because most definitely that is illegal. So with that all in mind, let's go ahead and learn how to build this. If you've been subscribed for a couple of months, or you just saw the video, then you know that in a previous video we made this. a $5 pocket taser. Now, since the video, as you can see, I made a few adjustments. Namely, this momentary switch is a much smaller one. And second, instead of two wires coming out of the top, I just cut off these two ends of these roofing nails to use as the two terminals on the top. And so, when connecting up a 9-volt battery, we can go ahead and click this and generate quite a powerful arc of electricity. So in this video, we're going to be using that high voltage pulse coming out of this $5 pocket taser in order to generate an EMP. In the How to Transmit Energy Wirelessly video, we learned that a magnetic field induces a current inside of electrical wire, and that a current of electrons through wires induces a magnetic field. So with an EMP, if we can give a wire a lot of current at once, it'll build a stronger magnetic field for a fraction of a second. And if we take that wire and turn it into a coil such as this, the magnetic field is multiplied that much more. So by using this, we can make a strong burst magnetic field that will then induce a current inside of other electrical devices, thus frying them. Now, to produce an EMP, you'll normally see a circuit like this. You'll have 2 points for high voltage going into it. And then from there, normally it goes across. There's normally a spark gap around here. Over here, you'll normally have a capacitor, and over here is going to be your coil. And how this works is that when the high voltage goes across, it'll charge up this capacitor. And when the capacitor is fully charged up, it'll shoot all the current from the capacitor down through here and jump across that spark gap, successfully discharging the capacitor. From this, it'll send a huge spike in current across that coil, thus making a momentary magnetic field that grows and then collapses in on itself really fast. And so, as you can see from the schematic that I was referring to just a moment ago, here we have a spark gap, and over here we have the capacitor. And I actually have a couple more capacitors back here just to give it a little more of a high voltage buffer point. If you want to learn how to make these capacitors, we made that in the last video. A link for how to build these high voltage capacitors, this high voltage power supply, and the pocket taser will be down below in the description. When I flip this on, watch the multimeter and see what happens. As you can see, for that brief moment, it shut off the multimeter, and the multimeter restarted. Since these capacitors are charged up, you're going to want to make sure you have something safe to discharge it. If I were to leave it on for longer than just that brief second, it would probably destroy this multimeter. Since I don't want it broken, I'm not going to test that, but just know that that probably is what will happen. Okay, so now instead of that big high voltage power supply, I've connected it up to my small pocket taser. Let's go ahead and flip it on using the same spark gap as before and see what happens with the multimeter. As you can see, the EMP is working well. Okay, so now I'm going to be taking all of these things and putting them onto this board with the coil up here to make sort of like an EMP stick. I'm still going to use our homemade capacitors because that's something that all of you can do. However, if you've salvaged or just have ceramic disc capacitors such as these rated for high voltage so that it would take up less space than these big capacitors here. I'm going to be using this thing I had lying around for the spark gap. I'm not really sure what it is, but it should work fine. Now, one end of the coil needs to be attached to this other end of the spark gap. The other end of the spark gap needs to be attached to one end of your capacitor bank. And the other end of your capacitor bank needs to be attached over here to the other end of your coil. Now, when we attach alligator clips to either end of the spark gap here, and if we attach them onto the pocket taser, when we click it, we should see voltage jump across this spark gap here. And just as before, this is generating an EMP through this coil. Now I could attach these capacitors on the underside of this board, and it would be a functioning EMP stick. Whenever I bring this coil near to, it'll send an electromagnetic pulse through it, thus damaging the object. I would do this, however I have a better idea for a less powerful EMP, but more of a stealth pocket EMP to go along with the pocket taser theme. So I wound some enameled copper wire around this PVC tube here in order to give me a hollow enclosure along with the coil needed. My plan is going to be to take those high voltage ceramic capacitors I have and stuff them inside of here till I get the high enough voltage rating with the amount of capacitance I want, and then use the two nails up here for the spark gap. And when it's done, you should just be able to connect one wire from the capacitor to one end of this, and then the coil to the other end, and then slide this on top, and then you have yourself a pocket EMP attachment for your pocket taser. Now I'm going to simply stuff these capacitors inside the hollow shaft here, and then I have this wire coming out that I'll put down on the other side to attach the nails or the spark gap. Once you have those wires connected on up, you can take this plastic cover and slip it on over, and then you have yourself your very own pocket EMP. Now remember guys, this will mess up electronic devices. So don't use it around anything you care about too much, and especially don't use it around equipment that's not yours. The nice part about this though is that from the EMP, if you want to turn it back into your pocket taser, you just slide it on off, and make sure the wires come off with the nails. I had it loosely wound just barely, so that's why it came off so easily. And your pocket taser will be back to good as new. Okay, so final notes on this configuration. After some testing, I determined this is still a suitable way to generate an EMP, that is the cylindrical coil here. However, it's much more weak. I would show you guys with this multimeter here, however, I believe I have fried it. How I fried it was with this, and I left this EMP constant next to it for about 10 seconds, and it fried out the multimeter. However, I would say that this coil design is weaker than this coil design. I just think the pocket EMP attachment is a pretty cool accessory for the pocket taser. With that said, I only have one layer of wire going down this. You could probably make this coil better by putting multiple layers on top of it. So now you know how to build your very own EMP generator. Thank you all so much for watching the video. If you enjoyed this video, be sure to leave it a thumbs up. And if you'd like to get our weekly videos such as this one in your subscription newsfeed, go and hit the subscribe button below. Be safe, and have a wonderful day. You're watching Keystone Science, and in today's episode, we're going to show you how to build your very own capacitor. You're watching Keystone Science, and in today's episode, we're going to turn a microwave into a magnetron gun. Now first, let's go over a few things before we get started. Microwaves have a lower energy than light, and so don't be afraid that this project is going to give you cancer or anything like that just from the microwaves. Since the microwaves coming out of the magnetron resonate so well with water molecules, that if the microwaves hit you, they do have a chance to damage your cells, and if they hit your brain, they have a chance to damage that as well. And although you can't see it, I'm actually wearing tinfoil underneath my clothing. This way, the microwaves, rather than affecting your cells, would just be absorbed by the tinfoil. Also, another important thing is that due to this, the microwaves can actually make your eyes go blind. And so although we're going to be putting a waveguide on the microwave later to make sure the microwaves only go in one direction, until I do that while I'm testing, it might be a good idea to take the screen of the microwave and use it to cut out some goggles. And although it looks stupid, it might be a good idea to wear a tinfoil hat. So, second off, and as I'll show you later, the microwave that this is emitting will affect electronics. So if you have expensive electronics near it, like a phone or watch, you should probably set them aside so they don't get affected. And in case you're wondering, since the camera I have set up to record this is an electronic device, we're going to build something that'll direct the magnetron rays so they won't be hitting the camera. And second off, just as an extra precaution, I have parts of the camera wrapped in tinfoil to create a Faraday cage. So thus the internal components of the camera will be completely fine. And so here I have an old microwave that we'll be taking apart. First, before we start disassembling this, make sure that your microwave is plugged out. So now I'm going to cut to where I already have removed all the screws holding the frame. Once you have all the screws removed, the outer layer should just peel off. And that should expose all the components that we'll be needing. Now pretty much the main components we're going to be using inside of this is the magnetron, the microwave oven transformer, and this capacitor here. Also, while we're taking this all out, I'm going to try to keep these wires in the same connection. That way I can draw a circuit diagram based on what they already have built here. Now I've never seen something like this inside of a microwave before, but mine actually has a circuit diagram on how everything should be wired up. You can see it needs a magnetron, the high voltage capacitor, and the microwave oven transformer. To get the magnetron to work. Now I have the magnetron successfully taken out of the microwave, and I attached a wire attaching the frame of the magnetron back to the microwave. So now I have my camera back about 5 meters, and I'm going to leave it and the microphone back here while I go over there and turn it on to see if I can get a light bulb to light up. So now we're going to go ahead and also take out this microwave oven transformer as well as this capacitor. Now although these kind of capacitors have a bleed resistor inside of them that will discharge them as they sit here, it's good practice to go ahead and discharge them to make sure you don't get shocked. And so to do this, you can attach an alligator clip to one of these capacitor terminals and touch it to the other side. And so you should see no spark since this has the bleed resistor inside of it. But if you do have a spark, then it's very good that you did that, because that would have shocked you. Okay, so now in designing our waveguide for the magnetron, we need to know a couple of things. First off, the frequency that the magnetron outputs is around 2.45 gigahertz. Now the formula to calculate wavelength is going to equal to the velocity divided by the frequency. And so since we're dealing with light, its velocity is just going to equal to the speed of light, which is about 3 times 10 to the 8th power. And so if we plug this all in, we get 3 times 10 to the 8th divided by 2.45 times 10 to the 9th. And now this calculation gives us approximately 0.1224 meters. And that's going to be equal to about 4.821 inches. And so we know basically a single wavelength, basically this portion of the wave, is going to be equal to about 4.821 inches. And so with this being our magnetron, we have two options. Right from the emission point, we could put a cone that goes up at around 35 degrees. Or in my opinion, the better way is that we could go out one wavelength of distance and then go up at around 35 degrees. And so building this frame here out of metal should give us protection from this magnetron, and also the waves will be stronger going out in one direction here. Okay, so now to make that little box at the beginning of the waveguide before I hit the cones, I drew this box onto the metal frame of the microwave that we had previously removed. When I measured the side lengths of my magnetron, it was 3 inches by 3 inches. And so from this point to this point, it's 12 inches long. And it goes down 4.82 inches. And so anyways, now I'm just going to cut along these black lines with these tin snips. Okay, so now with that piece cut out, I have lines drawn every 3 inches and I'll be able to fold it. Also note, I have about a half of an inch here, so I'll be able to fold it over. In order to get it nicely folded, I'm just going to place it here on the edge of the table, then push it down. Okay, so now with that piece folded over, you can see that we can just lift this up on over, and it should stay in place. And so going back to the magnetron, you can see how the box he made fits nicely on top of it. Okay, so now out of cardboard, I cut these two side templates out that I'm going to be using. If you want to replicate what I did, here are the dimensions for each of them. And if your magnetron is a different size, then you can times all the side lengths by the different size ratio. I'm now going to take these and try to fit them on from the cover of the microwave. But anyways, I'll be right back with you guys when these are cut out in metal. Okay, now I have the metal all cut out and it roughly put together. So anyways, now I'm going to take this metal enclosure and I'm going to go put some epoxy on it. But for the epoxy to set in fully, it's going to take about 8 hours, so let's go to that now. Okay, the epoxy finished setting, and after it did, I applied these strips of aluminum tape. Not only will these strips of aluminum tape make it so no microwaves can get out, but also they make it quite a bit more strong, as the epoxy alone was pretty brittle. Now our plan was to have this small box here and then put the top on like this. However, I figured it would be much easier to attach this to the magnetron if I used this. When we first opened up the microwave, this is what the magnetron was sitting in. And so I took my angle grinder and somewhat crudely cut out around it so we could pull it out. Now I know looking at this, you'd expect that the microwaves are being emitted out of this top part, but actually it's being emitted radially from this pink beryllium oxide. Now as you do this, be very careful not to shatter this pink part here, because this pink part might be made out of beryllium oxide, and if you shatter that and breathe it in, it'll be very bad for you. And I assume this angle is actually 35 degrees. And so that should mesh together quite nicely with the waveguide I have made. And so now I'm going to go ahead and attach this back onto the magnetron and screw it into place. Now next I'm going to be putting on this top part that I made. Now I would probably be using epoxy, but that's going to take too long to set. And so for now I'm just going to try to hot glue this on, although I know that that's going to probably fall off very easily. And now we have everything to direct the microwaves completely assembled. Now I'm going to attach the rest of the circuit onto this board. Now before we drill on the holes, there are two things we need to do. First, lightly sand the outside of the microwave oven transformer. We need to do this because there's an epoxy coating on the outside of the transformer. And by sanding it, it'll allow us to make a better connection when we connect it to ground. Now this that I'm going to put behind the transformer is optional. Basically, this is called a noise filter, and its main purpose is to produce a nicer sinusoidal wave out of the voltage going into it. And so this isn't necessary, but since my microwave had one of these, I'm going to be connecting it into it. And so first I'm going to drill on some pilot holes for the microwave oven transformer. Anyways, now I'm going to slip these two ground terminals onto this screw. And now with that done, I can screw it into place on the body of the transformer. And then on the other end of the transformer, I'm going to attach this wire with this tab onto it. For the capacitor that was inside of the microwave, there's normally this little casing that secures it onto the frame. And so now we're going to be using this little casing to secure it onto this wood. Since the magnetron is going to get quite hot while it's operating, I'm going to be using this fan to cool it down. And so for that, with this noise filter, I'm just going to solder it to the output wires in parallel. If you don't have this noise filter, you can just wire it in parallel with the mains power. Okay, and now with the fan screwed into place, all that's left should be attaching the magnetron. And so I'm going to use these small holes down here to secure it onto the board. And now all that's left for us to do is connect everything up. And so now we need to get the ground connection onto the magnetron. So I'm going to connect the free end of the diode onto the body of the magnetron. And then I'm also going to connect this wire, which comes from the body of the microwave oven transformer, onto the body of the magnetron. And lastly, we can connect these terminals into the microwave transformer, and then that connected back up to our noise filter. And now our magnetron gun should be complete. I added these two handles on the bottom just by cutting wood and screwing it onto the top here. Now something you guys really need to know is about the safety of this microwave oven transformer. That little transformer there outputs over 2,000 volts, and along with that it can output a very high current. In other words, if you touch the output of that transformer, you're practically going to die. And since the other end of the transformer is connected to ground, it's going to probably arc through you. So never under any circumstances touch any part of the circuit while it's turned on. Even on the low voltage side, it's still 120 volt mains, and that'll be very painful. And so with that said, I'll say to you guys, do not try this because it's very dangerous. Anyways, with that all said, let's go ahead and try this out on some things. Now, it's actually been pretty hard to find an area to test this out at. In fact, the only real safe spot I can do this at is at that Tesla coil back there. Whenever I point this in the general direction of a plug, the breaker instantly flips. So let's go ahead and try turning this on and lighting up this fluorescent bulb I have back here. As you can see, when I shine the gun at the bulb, it instantly lights up. And by the way, that sound you can hear is when I point it towards that plug. Now the microwaves shouldn't be interfering with the microphone since it is directional, but they might be. So as you can see, I get quite a range on this. Right now I'm about 2 meters away from that light bulb and it's still lighting up very well. Now, in case you're wondering why this microwave gun was able to light up the fluorescent bulbs, basically what's happening is the concentration of microwaves is ionizing the mercury inside the bulb. Basically, it raises the atoms inside of it up to a higher energy level, and then when the atoms lower back down to the regular energy level, they emit UV light. Then the outside of the fluorescent bulb is coated in material that lights up when the UV light hits it, so thus it sort of changes the UV light into visible light. Okay, so now to show you what this guy does to electronics, I'm going to turn it on and point it at this microwave oven timer we made in a previous episode. You'll only see it for a second, because when it does, it'll instantly flip the breaker. And since this microwave gun is connected up to the same system that breaker is, it should shut it off very quickly. So let's go ahead and give it a try. But it took a few seconds to shut it off just because it was practically warming up to start sending the microwaves. So now you know how you can turn an old microwave oven into a microwave directional gun. Thank you all so much for watching the video. If you enjoyed it, I'd really appreciate it if you leave a thumbs up, as it really helps the channel quite a bit. And if you'd like to see my weekly science videos, go ahead and hit the subscribe button so they'll show up in your subscription newsfeed. Since this is a dangerous project, if you don't know what you're doing, please do not try it at home. So with that in mind, please remember to be safe and have a wonderful day. You're watching Keystone Science, and in today's episode we're going to show you how you can transmit data through light. You're watching Keystone Science, and in today's episode we're going to be making a miniature ion propulsion device. Now before we get started, I did receive a couple more letters in the mail, so let's go ahead and address those. This first letter comes all the way from Australia, and it's from Taj Boss. And so he's a 12-year-old who's been working on some projects. And in fact, he showed one of the projects right here. That looks pretty cool. Anyways, he has also sent me a lovely picture, and that's right here. So thank you so much, Taj, for sending me this letter and this picture. It's very awesome. And our next letter comes from West Valley, Utah, which is just a little ways away from where I am. And he says he really likes the videos on radio transmission, and that him and his friends have tried to make a radio station, but the local regulations made it a little bit too hard for them. And so I'm sorry about that. I haven't really, to be honest, looked up many regulations in this area, so I don't know how many I'm breaking. Anyways, he also says that I should use one of those things, those weird devices, to hang up the letters rather than using a baseball bat. I'm not sure why. It seems more inefficient. But anyways, he also shows that he has a YouTube channel, and so that channel will be linked in the description below, and it says that he does gaming live streams and stuff with his friends, so that sounds kind of cool. You guys should go check it out and support him. So now I'm going to go ahead and hang these up on the wall that's over there. It's getting a little bit full right now, but there should be a place to put them. So now, before we get into making our ion propulsion device, let's learn what it is and how it works. Now, before we talk about how the ion propulsion actually works, we should probably talk about what an ion is, in case you don't know. An ion is just an element with a different number of electrons from the amount of protons inside it. So if it has more electrons than protons, it's going to have a net negative charge, and if it has less electrons than protons, it's going to have a net positive charge. And in fact, for oxygen, we see two common ions. One of them is going to be O2-, because that'll complete the shell that I'll show you guys in a second. And another one is just going to be O+, and that's just going to be because it completes a subshell. Now what I mean by shell is that the amount of electrons inside oxygen, since its periodic table number is 8, is 8. However, there are only 6 valence electrons, meaning electrons on the outside. So filling it in, we can see that there's 2 electrons here on the 1s orbital, 2 electrons on the 2s orbital, and then the 2p has 1, 2, 3, and 4 electrons. Now you may have noticed that I was filling it in left to right. That's because the electrons repel each other, and so they're going to want to occupy as far away suborbitals as they can before they have to get close to another electron. And so if we were to knock out an electron from this oxygen atom, we would see that this would be knocked out right here, and then it would be a little bit more stable because this subshell is complete. However, if we were to also add 2 more electrons, we'd see that this subshell would be completely filled up, meaning it would be a very stable atom. And in fact, in the periodic table, we call these noble gases. Not the ions, I mean, just 8 valence electron atoms. So how can you use turning an atom into an ion to propel something? Well, as we look at the positive charge here, what's happening is that the electrons are being pulled away from the atoms inside of this. And that also creates a net positive charge up here. And from that, down here, we have the similar thing happening where the electrons are going to be pulled up to the top here. And then when the electrons fly through the air, they're going to be hitting off electrons from other atoms, turning them into ions. In fact, we can calculate the amount of ions that we can be creating with certain energy and the momentum of the electron going off by using the electron work equation. And so if you're curious, that equation looks like this. We have the amount of energy required to knock off the electron, and that's going to be negative, and we're going to be subtracting that away from the total amount of energy we have going into the system. And that's going to be equal to 1/2 mass times velocity squared. Now the mass here is going to be equal to the mass of the electron, which is 9.01 approximately anyways, times 10 to the negative 31st power. This is a constant that's going to be different for every element, and even depending on the state of the element, because the first ionization might not be equal to the second ionization. In fact, it most definitely won't be equal to the first ionization energy required, and so you're going to pretty much have to look that one up. But by computing all this, we can figure out the velocity and use that to figure out even the momentum of the electron that's going to be leaving the atom. This is one of the factors that contributes to a little bit of the thrust, but it's practically negligible compared to the other factors. And so going back up here on this sharp object, we have an increasing positive charge as the electrons get drawn away, and this negative charge is also increasing as the electrons build up on the top here, drawn to that positive charge. And across this, we're going to have sort of dielectric effect, creating a capacitance. If you want to learn more about capacitors, I made a video on capacitors a little while back, and so I'll have that linked in the description below, so you guys can learn a little bit more about this force. But it basically uses Coulomb's law and all of that just to sort of have a difference in charges and that attraction between them. And so from that electron zooming across, it's going to knock off one of those electrons from, for instance, the oxygen atom. And when this happens, it's going to have a net positive charge on the oxygen atom, since there are going to be more protons than electrons. And since it has that negative charge, it's going to go zooming towards the negative charge one because that's what it's drawn to. However, rather than hitting it, a lot of the times it's going to miss it slightly and just create this momentum going this direction. And that is where most of our propulsion force is coming from. So in simple ways, that's pretty much how an ion propulsion motor works. Although ion propulsion doesn't really generate enough thrust to get a satellite through Earth's atmosphere and out of Earth's gravity, it does, however, inside of the vacuum of space, create a very nice way to reach insanely fast speeds. A major difference, though, from here on Earth and in space is that in space, there's not going to be quite as many atoms floating around. In fact, it's going to be near zero since it's practically a vacuum. And so to combat this problem, inside of the satellite's fuel, they actually just have a bunch of xenon. Now yes, xenon is a noble gas, so it is going to be harder to get that first ionization energy compared to something like sodium. However, unlike sodium, xenon is a gas and it's non-reactive, so it's not going to mess up the other instruments within the satellite if something bad happens. And they use xenon compared to something like argon or neon simply because it has more mass, and so for the amount of energy you're putting into it, you get around twice as much thrust as you would from something like argon. Now this works in practically the exact same way as I showed above. You basically have the xenon atoms going in, then passing through this high voltage chamber, which is going to ionize it. Then the ions are going to be attracted to the negative grate, which are then going to pass through, and then as they fly out, it's going to provide a forward momentum for the satellite. And so hopefully now you guys have a general understanding about how ion propulsion works. And so let's go ahead and build a little model of an ion propulsor. This model of an ion propulsor that we're going to build is a very popular model called an ionocraft. Now this model has been being made for a long time as far as I can tell. However, the first time I was exposed to it was from a website called ribstar.org, and he also gives instructions on how to build it, and so I'll have that linked in the description if you guys want to check it out. But basically it's going to look something like this, where down here is going to be aluminum foil, and then up here we'll probably have a thin gauge wire, so probably like 32 gauge. And so the wire on top is going to act like a sharp point, while the aluminum on the bottom is going to act like a rounded spot. As I discussed earlier, the amount of thrust produced by this is extremely low, and so we're going to want to make this as light as possible. In past iterations of this that I built myself, I've actually even used spaghetti noodles for this. It was pretty delicate though, and so this time I'm just going to be using balsa wood, which is still very delicate, but should hold up better probably and look a little bit more presentable. Anyways, this top wire is then going to be connected to our high voltage positive, while the bottom here is going to be connected to the high voltage negative. And then from this, we should be able to see it lift off the ground. And so let's go ahead and build this module here. To start off building this, I cut out this piece of aluminum foil. It's around 30 centimeters wide and about 5 centimeters in width. And so now I'm going to cut 3 increments of this balsa wood at about 9.75 centimeters each. Now as you can see, I have them positioned in such a way that this will be able to fit in between them. And so now I'm going to use some of this super glue to glue it down into this positioning here. This way we'll be able to fold it over, and then we'll put in these 3 prongs, and then we'll be able to fold it up into the triangle shape. Now that it's super glued into place, we just need to take this aluminum and fold it over the balsa wood like so. This way we'll be creating that round surface that we need. Okay, cool, right? Simple enough anyways. Let's go ahead and cut some more balsa wood. Okay, so now I'm just going to go ahead and cut 3 more 12 centimeter segments of balsa wood, and these will act as the 3 prongs to hold it up. Okay, now I'm going to fold this over onto itself, and then using that little gap, I'm going to put that aluminum over here, and then glue it into place, making an equilateral triangle. Now the last thing we need to do is glue our 3 balsa wood supports into the corners of the equilateral triangle. And so I find it best to probably glue it up around that far up the base, but you guys can do it differently. It's not a super solid science. And so, yeah. And now with 3 posts glued into place, we just need to attach that sharp terminal end that the positive wire will be connected to. In order to do that, I'm going to be using this 32 gauge magnet wire. So I'm going to go ahead and get a length of it, and then while leaving around a foot of wire, I'm going to go ahead and sand all the enamel off the rest of the wire. This way it'll be able to make a nice connection point between the air, because as the magnet wire currently sits, it has a glass enamel coating over it to make sure that it doesn't conduct with itself when you're making, for instance, coil. And that's why it's called magnet wire. But yeah, just go ahead and sand off that enamel. And so I'm just going to go ahead and start by winding one loop around this first post, and then a second loop around this second post, and then a third loop around this third post, and then I'm just going to bring it back over to the first post with one more loop to connect it up. As you do this, try to make sure that the wire is positioned vertically evenly throughout, as that'll make it kind of work quite a bit better. So yeah, make sure you do that, otherwise it'll be a little bit more erratic. The final thing we need to do is take a wire and connect it up to the aluminum skirt that wraps around it. And so I'm just going to use a little bit of Scotch tape to do that. And there we go. This wire is going to be what we connect the high voltage negative to, while this wire is going to be, of course, the high voltage positive. And with that final step done, our ion craft is complete. Now, of course, you do need a high voltage power supply that outputs a DC high voltage to run this. If you need help on trying to figure out how to make that, I have made a few videos showing how to make a few different variations of a DC high voltage power supply, and so I'll have those linked in the description below. Okay, now I have it all hooked up, and as you can see when I turn on the power, it generates a little bit of thrust. Also kind of fun, if you can see in my oscilloscope in the background, whenever I connect up the power, it wirelessly picks up the energy, and you can see that sine wave given off. And also it looks kind of, oh no. Well, I'll fix that, I guess. See, that's probably happening because I'm trying to run it off of the thing that ran my arc glove, and I'm guessing it's allowing a bit too much current to pass through. So that when it does get a little arc like that, it just jumps up and draws a lot of current, and that is way more than enough to light the balsa wood on fire. Okay, so now it's fixed and it's working properly. I have it tethered down because it was just keep on flipping over and such like that. And so I'm actually using the same power supply that I was using before. This is version 3, though, of the one I've made, just because the other two have gone up into flames, because when it would arc over, the plasma would be hot enough just to light it all up. And so yeah, let's go ahead and take a look at it. As you can see, right when I apply the power, it creates that force and it just floats up off the ground. And I imagine it could float a little bit higher probably if I more optimized where the wires were. And also it's tethered down so it can't float that high, as you can see. So yeah, that's kind of cool, I think. And it's definitely a pretty good demonstration. Let me go ahead and turn off the lights just so that you guys can see the purple corona given off by this as it goes. And hopefully it should look pretty cool. So yeah, just 1 second with that. Okay, so it's kind of hard to see. But if you look closely, you can kind of see the purple glow given off by where the electrons are jumping off the metal. I was expecting there to be slightly more corona, but I suppose this is good because that means that it's nowhere near arcing over, because arcing over is then what causes it to burst into flames. So it's good that there's this little corona, but it also means that I could probably move the wires all down a little bit to get a little bit more thrust going upwards, and that would probably give us more corona. I just don't want to risk it just because of the fact that it keeps on going up in flames. So yeah. Okay, so one last thing I should mention in this video. So this does require a very high voltage, and if you were to touch it, I don't think it would kill you because I touched it earlier and it just left a big burn mark on my finger, which isn't here because that was a couple days ago. But it does hurt very bad and could possibly kill you if it shocked you in the right place. So do not basically do this unless you have proper training and proper safety and all that. Yeah. Okay, also one more thing. So I have a candle here, and I just wanted to show you guys the ion wind given off by this. So let me go ahead and light this. So as you can see, the flame of the candle is obviously being affected. In fact, that just really blew it out because of all the ions basically flying down and hitting into it. In fact, an interesting thing, if you could see that, was that the smoke, I believe, would have been drawn up towards one of these because the smoke in itself is also ions. And so yeah, that's kind of interesting, I guess. So now you know how an ion-powered thruster works and how you can build a very simple model of one. Thank you guys so much for watching the video. So a quick heads up, next episode we are going to have a giveaway because the company actually sponsored to have a few pocket oscilloscopes given away to some of you guys. And so yeah, in the next episode, leave a comment below if you want to be in that. But anyways, if you enjoyed this video and or learned something new, I'd really appreciate it if you'd hit the thumbs up button as it really helps the channel. And if you'd like to see my science videos, go ahead and hit the subscribe button so they'll show up in your subscription newsfeed. Also, a special thanks to all you Patreons who help make these videos possible. Their names are right here if you want to see them. If you have a suggestion for a video you'd like to see in the future, go ahead and leave it in the comment section below. And so that's all I have for you guys this week. Please remember to be safe and have a wonderful day. You're watching Keystone Science, and in today's episode we're going to show you how to make a very simple plasma arc lighter. You're watching Keystone Science, and in today's episode we're going to show you how a theremin works and how you can make your very own. Alright, so before we get started on today's project, we do have a letter, so let's go ahead and take a look at that. So this letter comes from Adam Thomas in Denver, Colorado, and he tells me a lot of things that he does, including trying to raise more awareness for recycling, which is definitely a really good thing, so good job with that. Also, he says that he has his own YouTube channel called Chalk Motion Science, so I'll have that linked in the description if you guys want to go check it out. Anyways, he also drew this really cool picture for me, and so thank you so much for this. And so I'm going to take these and hang them up on the letter wall back there. Okay, so let's jump straight into learning how a theremin works before we actually build it. Now there are two things mainly that affect how the theremin works. First off is a thing called You're watching Keystone. You're watching Keystone Science, and in today's episode we're going to show you how a theremin works and how you can make your very own. Alright, so before we get started on today's project, we do have a letter, so let's go ahead and take a look at that. So this letter comes from Adam Thomas in Denver, Colorado, and he tells me a lot of things that he does, including trying to raise more awareness for recycling, which is definitely a really good thing, so good job with that. Also, he says that he has his own YouTube channel called Chalk Motion Science, so I'll have that linked in the description if you guys want to go check it out. Anyways, he also drew this really cool picture for me, and so thank you so much for this. And so I'm going to take these and hang them up on the letter wall back there. Okay, so let's jump straight into learning how a theremin works before we actually build it. Now there are two things mainly that affect how the theremin works. First off is a thing called resonant frequency, and the second is a thing called capacitance. Now in the case of electronic circuits, resonant frequency is most commonly used to describe the relationship between having an inductor and a capacitor in parallel. So to understand this, we have to understand inductance and capacitance. So an easy way to describe inductance is if you were to imagine yourself winding a wire around a nail. Most people have done this, and then when you connect it up to a battery, it becomes an electromagnet. Well, when you disconnect the power, what happens? So what will happen actually is that the magnetic field will collapse back down in on itself, thus creating current of electrons through the wire. And so when we have that in parallel with the capacitor, it's going to then put that charge into the capacitor. Now capacitors work kind of like a static electricity. So if we have two plates, one of them is getting more and more positively charged, the other one's getting more and more negatively charged. And so the inductive spike basically is going to flow back in and charge up the capacitor. And then the capacitor is going to discharge through the inductor, making a magnetic field, and they're just going to go back and forth, slowly decreasing in power since they're not going to be 100% efficient, but it's going to oscillate at a certain frequency. And that is what we call a resonant frequency. So hopefully that description made sense to you. Let's go ahead and look at it using some math. Alright, so first let me draw out what I was talking about before. So we have the coil right here, and we have it in parallel with the capacitor, and then basically putting electricity in through here, like that. And then when we were to disconnect the power, it would start oscillating at a certain frequency and then slowly decrease in power and eventually get out to pretty much nothing. And yeah, that's going to be the resonance. So the formula for resonant frequency using a capacitor and an inductor is going to be the resonance frequency is equal to 1 over 2 pi times the square root of the inductance times the capacitance. Now, inductance is measured in a unit we call henries. And so in this specific circuit that we're going to be using, it is going to be a 1 millihenry inductor, which is 1 times 10 to the negative third, and the capacitance is going to be 150 picofarads, which is 0.15 times 10 to the negative ninth. And so now we can apply this formula to this, and then we can see kind of what frequency we'll be generating with our circuit. So we have 1 over 2 pi times the square root of 1 times 10 to the negative third times 0.15 times 10 to the negative ninth. And then once we plug all that together, we get around 411 kilohertz. So that's the first bit on how the theremin is going to be working. So let's go ahead and draw this as a block diagram here. So here we have the 411 kilohertz. Here we have the 411 kilohertz. And we'll say that's just the capacitor for that part. And that's the capacitor for that part. Just because in our specific theremin circuit, the inductance won't be changing, but the capacitance will be changing actually. And so what's happening is that these two frequencies are being meshed together, and then the difference between them is going to be outputted, since up at the 411 kilohertz, it's definitely out of the audible range, so we need to get it down somehow. And so we're combining these two oscillation frequencies into something. And so ideally, when we have nothing, it would be net zero. Over here, we have a variable capacitor. That's just because we're going to be able to tune it, because depending on different environments such, the capacitance rates will change. Because on the right side here, we have our antenna. Now what the antenna does is basically create a pseudo-capacitance between you and ground, since the whole circuit's going to be connected up to ground. And so the capacitance generated between the antenna, which will count as one side of the capacitor, and you, which will count as the other side of the capacitor, is going to slightly vary the net capacitance of this, which will then slightly vary the resonant frequency, which will then manifest itself in a frequency given out when we combine them both together. If you want to figure out the capacitance between the antenna and yourself, you can use this formula. So we'll say the capacitance of the antenna is equal to the dielectric times the area divided by the distance. And so the dielectric is basically just a constant, so that would be the dielectric force of air, which I'm not sure what it is off the top of my head. It's probably somewhere near 1. Yeah, okay, I just looked it up. At 1 atmosphere of pressure, it is like 1.00059, so practically 1. And so that formula, when you plug that all together, so we have 1 times the area of basically the plate exposed and your hand, the net area anyways, and then over here divided by the distance, which is just going to be in meters separating yourself from the antenna. Now the formula for calculating the capacitance in parallel is kind of the opposite of the resistors way, so that's going to be just the first capacitance plus the second capacitance equals the total capacitance. And so our brand new formula that we can write for the resonant frequency is going to be resonant frequency equals 1 over 2 pi times the square root of L times C1 plus, oh, and there should be parentheses here, L times C1 plus the dielectric times the area divided by the distance, close parenthesis, and there we go. That is our formula. It's kind of bled into the second part here, but yeah, that's the general formula to calculate the resonant frequency of this, and then you could use destructive interference to then minus that new one from this one, and that'll give you the output here in the frequency that you'll be hearing. So now that we know how a theremin works, let's go ahead and build one. Here's the circuit that we're going to be using today. Now this theremin is actually just going to be pitch only. It's not going to have a volume antenna. Quite frankly, just because if you had a volume one, the circuit gets a lot more complicated, pretty much too complicated for a regular YouTube video. Like, it would be a pretty long YouTube video with a volume antenna. But if you guys want, I can show you how to make one of those in the future. Anyways, I did not make this circuit. I did make small tweaks to it, but the original maker of this circuit is linked in the description below. Now this part over here is going to be the main bulk of the focus. The part that I have down here is simply just an amplification circuit, which you don't really need if you're going to be powering it with an external amp. Then you're all fine. But that's just if you want it to be in a self-concealed unit. Also, if you can't read the circuit from my handwriting, I do have the digital version of the circuit linked in the description, as well as the entire parts list for this. So yeah, you should be good. Now we have 3 pretty uncommon parts that are used in this circuit that you don't really see in too many other places, or at least for circuits that we have worked on so far. 1 is the variable capacitor, 2 is going to be the inductors, and 3 is going to be the JFETs. Now probably most any JFET will work for this circuit. At least try to have the 2 end ones identical for that similar frequency thing I was talking about before, just because the properties might alter something a little bit. The middle one could probably be different from the other 2, but it's probably best to have them all 3 identical. Anyways, the JFET that I'm going to be using in particular is the only one I could find inside my local electronics shop, and that's going to be the TI S58. And if you're curious, it just looks like this, just like a little guy. It kind of looks like a 2N3904 transistor, so yeah. And if you're following along exactly with me, then the pinout for this transistor, if you face it this way with the flat end facing you, is going to be drain, gate, source. And if you're wondering what drain, gate, and source are, based on the diagram below here, I have it drawn out here, where this end is the gate, that's the drain, and this is the source. Okay, so now that we have the JFETs talked about, let's talk a little bit about the inductors. Now, inductors themselves can come looking in many different ways. For instance, this one's just a coil wrapped around, I think, a ferrite tube in the middle, and I think it looks kind of cool because it looks all old-fashioned. And so, yeah, this one looks kind of more like a resistor, and these other ones just look more like the typical inductors that you would see inside of something just to smooth out a current. And finally, that leaves us with the variable capacitor. Now, variable capacitors are actually quite expensive. For instance, this could probably cost you like $3, which is expensive in my opinion for one component. It's about the same as like a MOSFET if you were to just buy a single MOSFET off the internet. But anyways, they can also look like this. This one's quite a bit more expensive. It costs probably like $15. But if you don't want to buy one, there is a way to make your own. I won't show you in this video, but I have seen videos on the internet, and I'll have them linked in the description below. Basically, they're either making a tube-style capacitor, which I've showed made in a video before, or they're basically wrapping foil around a cup on the outside and then a cup on the inside. So when you turn it, it's basically exposing more of the foil covering each other. And in that formula I talked about earlier to calculate the capacitance, it's that same principle where the different amounts of layers of the foil covering each other is going to be creating the varying amount of capacitance. So yeah, obviously the cleanest solution is going to be using something like this so that it fits nicely on a circuit board. Okay, that was all the preliminary stuff. If you didn't understand some of that, don't worry, you can still follow my steps step by step, and you should be perfectly fine. So let's jump into building this out onto a breadboard. Alright, so the first thing we're going to do is place down this 100 ohm resistor, and so we'll bring that from the positive rail over to just an open rail over here. And now looking at our circuit, we can see two things are directly connected up to that 100 ohm resistor. First is going to be the 10 microfarad capacitor, and second is the 1 millihenry inductor. So first I'm going to take the 10 microfarad capacitor and connect the positive end to the 100 ohm resistor and the negative end to an open rail. And then I can take my 1 millihenry inductor and connect it up one end to the resistor and the other end to an open rail. Okay, so you can see that whole circuit on the left side is pretty much centered around the JFET. And so for simplicity, I'm going to put it on these rails down here, then we'll use jumper wires to connect up those components to the JFET. And so now we can take a wire from the negative of that capacitor to the gate of our JFET, which for me is the center pin. And next I'm going to take a jumper wire going from the open end of the inductor to the drain of the JFET, which for me is this first pin right over here. Now on the circuit you can see that from the drain to the source of the JFET we have an 150 picofarad capacitor, and then from the source to ground we have a 1.5 nanofarad capacitor and also a 470 ohm resistor. And so let's go ahead and insert those now. Now I'm going to insert the 150 picofarad capacitor, which is marked as a 151 on the capacitor code between the source and the drain of the JFET. And now from the source of the JFET I'm going to connect that 1.5 nanofarad capacitor going over to the ground rail, and also the 470 ohm resistor going from the source over to the ground rail. And finally, we need to connect the gate of the JFET over to the ground rail as well. And now with that step done, everything from the left of my pen is complete, so we just need to deal with all this stuff now. And so the first thing I'll do is connect up the variable capacitor to the secondary side of the inductor, and then the other side of that capacitor needs to be connected over to the ground rail. Now the next thing we need to do is connect up our 3.3 picofarad capacitor from the secondary side of the inductor to an open rail. And now from the new open rail from that 3.3 picofarad capacitor, we need to connect a 2.2 kilo ohm resistor from that going over to the ground rail. And now for this next part, we're centered around the middle JFET. And so I'm going to use the same trick as before, where I'm going to be putting it on the rail beneath and then connecting it with jumper wires, just because I think it's easier for you guys to see what I'm doing that way. And so I'm just going to insert my JFET on these open rails right down here. And right away I can take a jumper wire from my 3.3 picofarad capacitor rail over here, going to the gate of my JFET. Next I'm going to go from the positive rail to an open rail down here with an 8.2 kilo ohm resistor. And I'm going to follow that up by placing a 1.5 nanofarad capacitor going from the positive rail to that same rail I connected the 8.2 kilo ohm resistor to. Now we can take a wire going from this rail over to the drain of our JFET. Now I'm going to put another 8.2 kilo ohm resistor going from the source of the JFET over to the negative rail. And also on the source of this JFET, we need to connect the positive end of a 10 microfarad capacitor and put the negative end at the negative rail. Okay, now with that step done on our circuit, we're done with everything behind this point, except for we haven't put in that 10 microfarad capacitor yet, just because I actually didn't end up using that in my original version, just because that's the audio output, and I found it wasn't really necessary and didn't really change that much. But I will do some testing in a little bit, and that's just where it is if you want to put it in later. But now we're just going to focus on this side over here, which is practically a looped opposite of the beginning side on the left that we did, so let's go ahead and build it. I'm going to start by connecting an 100 ohm resistor from the positive rail to an open rail down here. And now, just as before, we're going to connect up our 1 millihenry inductor from that resistor going over to an open rail, and also the 10 microfarad capacitor with the positive end on that resistor rail, and the negative end just on an open rail over here. These guys are all centered around our final JFET, so I'll just put that down here so we can use the jumper wires again. And I can start by taking the negative end of that 10 microfarad capacitor and connecting it to the gate of our JFET. Now we need to take an 150 picofarad capacitor and connect it between the drain and the source of our JFET. And we can follow that up by connecting our 1.5 nanofarad capacitor from the source of our JFET to the negative rail. Now I'm just noticing this, but right here, there should be a 470 ohm resistor going from the source of that JFET over to the ground rail. And I didn't have that drawn in before. The one in the description will be the correct one still. But just from earlier, make special note of that, and let's go ahead and insert in that resistor. And so that guy can go from the negative rail over to the source of our JFET, and that's the 470 ohm resistor. Now we need to take a jumper wire going from that inductor over to the drain of our JFET. Okay, now the last thing we need to set up is the pitch antenna. And so as you can see, from that 3.3 picofarad capacitor, we need to connect that up to another 3.3 picofarad capacitor. Then that needs to be connected up to the drain of our JFET that we were just barely talking about, like the one on the far right-hand side. And then from there, we attach it to our antenna. So let's go ahead and do that. Okay, so now I'm going to take this jumper wire connected up to that 3.3 picofarad capacitor, and I'm going to bring it over here to this open rail so you guys can see the connections I'm making. And so now from that wire to the inductor on the far right-hand side, I just need to insert another 3.3 picofarad capacitor. And our antenna is going to be connected up to this rail here. And so now lastly, before we test, I need to go back to that middle JFET, and on the drain of it, I'm just going to connect this wire, and that's going to be our audio out, just so that it's easy to identify. And now finally, I'm just going to attach the antenna to this junction point between that 3.3 picofarad capacitor and the second inductor on the far right-hand side. And really, that's it to the circuit. And so now the very last thing we need to do for our circuit is connect up that audio output portion that I was showing you guys to an amplifier. Now guitar amps like these actually work really great for this because they have a high amplification value, so you can really easily hear the theremin, and it's pretty easy to connect up to. However, I'm assuming that most of you probably don't have one of those around, although you could just use a regular stereo system and connect it up, or any amplification system. Maybe your laptop could amplify it even enough. But let me show you guys how to make a quick external amplifier. And so here's our quick amplification circuit. Now this circuit is centered around the LM386 chip. It's a pretty common chip, so you should be good, and they're pretty cheap also. Anyways, the audio input is going to be in through pin 3. This potentiometer is just going to be adjusting the volume, and everything else is as put, with the pins connected as such. So we have 2, 6, 1, 8, 5, and 4. So let's really quickly build this. It should only take a minute anyways. Now first off, I should let you guys know what the different pins are on this chip. So if I face the divot, or sometimes it can have a dot in the upper left-hand corner. Anyways, if I face that upwards, then on the top left, we have pin 1, 2, 3, 4, 5, 6, 7, 8. And so we're just going to take that chip and insert it in between the two segments of the breadboard so that each pin is going to be touching an independent row. Now pin 2 and pin 4 are going to be connected to ground. So I'm just going to use this little piece of wire to connect both the pins together, so I can just use a single jumper wire going from one of those pins to ground, and it'll count for both of them. So let's put this jumper wire right here and just connect it to ground. Now I'm going to take this wire from pin 6 and I'm going to connect it over to the positive rail, and then also a 100 nanofarad capacitor going from pin 6 to the negative rail. Now I'm going to put the positive end of a 10 microfarad capacitor on pin 1 and the negative end of that capacitor on pin 8. And now from pin 5, I'm going to put a 100 ohm resistor going over to a free rail over here. And then from that free rail, I'm going to connect up a 47 nanofarad capacitor to ground. Now this capacitor value I left blank just because it's not really necessary. It's just a smoothing capacitor. But in my case, I'm going to be using a 220 microfarad capacitor. And so I'm just going to connect the positive end of that capacitor to pin 5 and the negative end to an open rail down here. Now I'm just going to take this small speaker and attach one end to that row with the 220 microfarad capacitor, and the other end is just going to go to the negative rail. And it's really just that simple. Our amplification circuit is now complete. Now I could have added the potentiometer between pin 3 of our LM386 and the audio output of our theremin circuit just to adjust the volume, but for this first testing, I'm not going to do that. However, in the final product, I will for sure add that so that it's not just making an annoyingly loud sound the whole time. So yeah, keep that in mind. Anyways, let's take the audio output now of our theremin, and we'll just connect it to pin 3 of our amplifier. Okay, I have it now connected up to our amplifier. Now, I did have to supply a secondary source of power because if I run it off with a common power supply, I was just getting some weird feedback that wasn't at all being affected by my hand position to the antenna. And so, but with it running off of a separate battery and just the audio in and not even being a common ground or anything, that's what causes it to work well. And so let me reconnect that up. There we go. And now you can hear my hand is changing the frequency of it. Now, if you're going to make it this way, you should keep in mind that I am using the separate power source, so you're going to need probably two 9-volt batteries, one to power this, both completely separated from one another. And also, I do have this running at 9 volts right now, just because I think that's what works best with this circuit currently, when it's connected up to this anyway, so that's what's giving me the best sound out of this. And so yeah, just keep that in mind. Let's go ahead and connect it up now to the guitar amplifier, and let's see if it sounds any better. Also, sorry if you can hear like a pittering, pattering. That's because now it's starting to rain outside along with the thunder. So yeah, that's what that is. Let's go ahead and move on. So it is definitely pretty stormy out here. There should be lightning sound in a second. Oh, yep, there it is. Whoa. Yeah, it's pretty stormy. I'm going to go back in and continue working on the theremin. Yeah, wow. Okay. Still going. Yeah, okay, back to the theremin. Okay, so here I have it connected up to the amplifier. It's running at about 4 volts right now, 4.1, just because in the way I have it tuned, that sounds nice right now, because it's a little bit difficult to tune. But as you can hear, as I get my hand a little bit closer, we start getting a nice low note, and the closer I get, we get exponentially higher. Yeah, it's kind of fun to play with. Now something kind of interesting, listen to what happens when I touch this other end of the 3.3 picofarad capacitor. I don't know if you guys can hear that, but I'm getting oh, there's some lightning outside, sorry about that. But I'm getting radio wave signals through. And in fact, if I take the antenna and input it there, then you can hear just the radio waves and you can't hear the theremin effect. Okay, now here's my sad attempt to play a song. Well, if you couldn't tell, that was my attempt to play Somewhere Over the Rainbow. Definitely didn't sound as good as this guy's. But whatever, you know, yeah. Anyways, let's go ahead and see what this circuit looks like when it's all soldered onto a PCB, so it looks a little bit better. And here's my finished product. For the audio out, I have this 3.5mm jack into the side of the case, and then for the regular power in, I just have like a regular DC power supply connector. And for part of the tuning, I put this small hole in the side to access the variable capacitor in which you can turn this in order to tune it. So let's pop this open and take a look inside. First, you can notice I have a whole lot of wire here. That's because the antenna I used is actually different from the regular one that I was using before. And so, in order to match its capacitance, I had to add all this antenna. Basically, before it was just getting way too high of a pitch based on my variable capacitor. So, if I would have designed it with this telescoping antenna behind it, or telescoping, or however you want to pronounce that, if I would have designed it with that originally, then the variable capacitor would have been one that offset it enough to get it into a nice range. But this added wire adds enough capacitance that it balances it out smoothly. And plus, it's already going to be all sealed behind, so I'm not really too concerned about that. Now, the pink wires are just to get to all the external components around here. Without the pink wires, it was just all one nice flush circuit board, but I guess that's what you have to do. And so I'm going to go ahead and seal this back up, and I'll show you guys how it performs. First, I'm going to plug in my power supply. Currently, I have this power supply at around 6 volts. It could really be any adapter that you find from at least as it's as low as 12 volts. It would just be a little bit more difficult to tune based on what I have noticed. And next, we can plug in the cable that goes to the audio out. And now we should be good to go. I'm going to go ahead and turn up the volume a bit. Okay, so now you can hear that I only get a sound when I touch it. That's because part of the tuning is extending the antenna to the right length. So let's extend it, for instance, this far and see what we get. So that's a bit much. Let's put it down a little bit. That's a little bit better, maybe a little bit more extended. Yeah, that's kind of nice, I think. So I'm actually getting a little bit harsher of a sound with this setup than I did with my previous setup. Not that the circuit at all changed, it's just that the capacitances are a little bit different, thus giving me a little bit different of a tone. But I still kind of like it. It's fun to play with. So now you guys must know the principles behind how a theremin works and how you can build your very own. Thank you guys so much for watching the video. If you enjoyed it and or learned something new, I'd really appreciate it if you leave a thumbs up, as it really helps the channel. If you have an idea for a video you'd like to see, go ahead and leave it in the description below and I'll try to get to it. Anyways, that's all I have for you guys today. I hope you guys have a fun time building the project and playing around with it, or even just learning how it worked. So please remember to be safe and have a wonderful day. You're watching Keystone Science, and in today's episode we're going to make a pocket analog oscilloscope. You're watching Keystone Science, and in today's episode we're going to be building a very, very simple AM radio. Before we get into the video, let's go straight into the mail. So today's letter comes from Daniel Mueller of Morton, Illinois. So here he says that he is a chemical researcher who dreams to share his interests of science with the world. And he says that he has been making YouTube videos. Does he? And he says that he would like to go onto YouTube to share his experiments on there. And as for the rest of this, I'm not sure if it's necessarily stuff that he wants me to read on the video, because it's mainly just trying to contact me, I suppose. So yeah, thank you so much for the letter. Also inside the letter, he gave me his business card, and he gave me this cool magnet, which has his logo on it. So that is definitely really cool. Let's see if it'll focus on. I have to hide my face. So yeah, thank you so much for the letter, Daniel. I will definitely send you an email. Let's go ahead and hang this up on the wall. I'm running out of stuff to hit. Alright, so now with that done, let's jump straight into the video. Now first I'm going to teach you guys the science behind how an AM radio works, just because I feel like that's the more important part, at least in my opinion. And so yeah, let's talk about that first. First, let's talk about how the signal is transferred from the transmitter to the receiver. And so this guy will be our transmitter, and this guy will be our receiver. Now obviously this is a very simple circuit diagram, and this is not actually how it's done, because you can see there's no power input or no place for the audio to be connected up to. This is just for a simple representation along with for the receiver here. First, let's talk about the transmission side. Now we have actually made an AM radio transmitter before, and so the link for that video will be in the description below. However, that was not made using a capacitor-inductor relationship. That was more made using a crystal oscillator, which is good, but this is better for the understanding of what's going on right now, I feel like, so we'll talk about this. First, let's go ahead and work our way through the circuit. So say if I were to apply a positive charge here, what would happen is that basically that would charge up the capacitor. Trying to think of a capacitor as basically the same kind of thing as when you walk across carpet and you touch a doorknob and you see a spark. You're becoming positively charged, and the rest is still kind of neutral, but technically it becomes more negatively charged, but on a very minute scale. So here, with the capacitor, if we apply a current and a voltage potential, then this side, let's say, becomes positively charged, and this side becomes negatively charged. This means that this side is trying to adapt to that voltage potential, so the area of this plate over here is getting electrons dispersed evenly on it, which means, due to just electrostatic attractions, which is the whole kq squared over r squared equation, that's going to be attracting the protons on this side and repelling the electrons. So if we look at the atom, basically, on this side anyways, the proton will be kind of over here, and the electron cloud will be slightly more this way, giving us a dipole here, which basically, in turn, means that this side is becoming positively charged. Now let's say we disconnect the voltage potential from this. The capacitor is going to want to return to a neutral state, because that's where it's most happy. That's where the atoms themselves feel kind of, in a sense, the least amount of stress. So this side's going to want to become more positive, and this side's going to want to become more negative, but in this sense, our electron is our charge carrier, and so the electrons are going to flow through here, through the inductor, and back around here. An inductor is basically just a coil of wire, and so you may have noticed, if you've ever wrapped a coil of wire around something like a nail, for instance, and if you attach a voltage across the coil of wire, you can see that then you can pick up paper clips and stuff with it, because it generates a magnet. So in this sense, as we have current running through this inductor, we get a magnetic field built up, and it will reach its peak when this becomes neutral. Now, since our circuit has become neutral and there's no flow of electrons through here, this cannot maintain its magnetic field, because that was simply put forward by the flow of electrons through it. And so that magnetic field is going to collapse back down. And as it does that, it's going to push electrons inside this coil in an opposite direction to the direction of the current, which is Lenz's law, if you have heard of that. It's basically the same thing that I talk about in my induction heater video, if you want to go watch that. This current will continue until the magnetic field here has completely collapsed in on itself, in which case, now we have no magnetic field, but up here, we will get our charge on the capacitor again. And then, of course, then the capacitor will dump its charge back into the magnetic field of the inductor, and it will create the magnetic field, and it will collapse in on itself, and it will oscillate back and forth. So this, in turn, if we were to look at the voltage over time, we would see it looking like a sine wave, as the voltage became negative and positive as the current flew this way, and then went this way, and back and forth it goes. Now, capacitors and inductors actually do have timing associated with them for the discharge and the magnetic field collapsing and forming, and so this gives us a frequency for that sine wave, and that frequency is simply equal to 1 over 2 pi times the square root of the inductance times the capacitance. So how does this relate to our radio? Well, this is actually the exact same frequency that you're tuning your radio to. So for instance, an AM radio that is at 1 megahertz is just the frequency of these two oscillating at 1 megahertz. And so here, if we have this wire attached, it's going to be leeching off a little bit of the current each cycle and creating, due to the same reason as this inductor, since this is technically an inductor, even though we don't have any coils there, so it's a pretty weak inductor, but it is an inductor nonetheless. And this is our antenna, by the way. And so around it, we are getting a circular magnetic field that's curled in the direction of the current. So if I have current going up this way, the magnetic field is going to curl like that. And similarly, then as the current flips the other way, it's going to curl in the other direction and have a magnetic field curling like that. So going back up to our circuit, we have this magnetic field, which is oscillating throughout here, and that means that it'll have an effect on this wire over here. So now this alternating magnetic field will induce an alternating current inside this other circuit over here. So now you may be wondering, hey, there are a lot of radio signals out there at tons of different frequencies, so how does the circuit know how to differentiate between them? And it's kind of a beautiful symmetry that happens in most things that you can observe. And so on this side, we have that inductor-capacitor pair creating the signal. And on this side, we can have that exact same inductor-capacitor pair that then has a resonant frequency at that same signal. So if we put power into this side, we generate a signal. And if we don't put power into this side, we adopt the signal into it. And since it resonates at that frequency, we get most of the frequency being manifested as that frequency transmitted here. Now, obviously, the other radio waves will make a slight difference into it, but nothing really noticeable considering that all the rest are kind of like destructive interferences with themselves, while this one is very, very, very clearly resonating with the circuit. So now that we understand how the signal is transmitted from the transmitter to the receiver, let's talk about how the signal is kind of encoded into the wave that is being transmitted. Now, a very similar experiment to this is kind of what I did when I was transmitting music through light, or music through, for instance, a laser is what I used, and I've also done it with music transmitted through LEDs, which I will have video links in the description if you want to view those. Now, this is very similar to how I was doing it for the light. And so basically, if I were to add another coil onto this side here, so let's add him in right there, and then if I were to add another coil right here and attach this up to an audio source, then we would see that we have a coupling between these two coils as their magnetic field generated produces a current in this one, and this one also does have a current effect in this one, but we'll not worry about that right now because that's not being put into our signal being generated. So if I apply audio here, which is an alternating current, we get a changing magnetic field here, which either impedes opposite to the direction of the current flowing here or helps it go forward, which means that we have more power flowing into the circuit or less power flowing into the circuit. So now with this added audio input, if we were to probe the circuit, we would see that the frequency would be the same because that's what it oscillates at. However, we would see a change in amplitude, which would mean that we would see something that looks like this. And the amplitude is changing because that is directly proportional to the current flowing through the circuit, which is then also affected by the audio thing here due to that coupling that I was talking about just a moment ago. Now, the process of doing this is called amplitude modulation, which is directly tied into how AM radio has its name, because the AM stands for amplitude modulation. In order to keep this project very simple, we're going to be building it on this 3D printed base designed by 3D Sage. Now, you can download this STL file on Thingiverse, and so I'll have that linked in the description below, and I'll also have his YouTube channel linked in the description below, because he makes some pretty cool builds, and this is very, very cool, as I've never seen anything like it. But if you don't have a 3D printer, and if you can't find a service that will 3D print it for you, then you can go along building this project with just, for instance, a PVC pipe to wrap the coil of wire around, and just very simple adjustments made. But basically the exact same premise, so don't worry too much about that. Now, I personally was able to 3D print this because the company Gearbest sent me a TiVo Tornado, which is a very good 3D printer in my opinion, and I would like to make some more videos showing its capabilities, but some things that I've 3D printed already with it include this Klein bottle, which is basically a mathematical shape, this bust of Einstein, which is pretty cool, this bust of Nikola Tesla, which is also fairly cool, and this Pythagorean cup, because, well, if you don't know what a Pythagorean cup is, it's basically if I fill up the water to a certain height, it'll all drain through the bottom because it has a water siphon induced into it. So, yeah, it is definitely fairly cool, and I'll be making another video giving a review of the printer in the future. The first thing we need to do is create our inductor, just like I was showing in the circuit. And so, for that, we're going to take this base off, and we're going to just wind a copper wire around all of this. Be sure that your copper wire is magnet wire, because otherwise it will conduct across it, and we need it to be able to form that magnetic field we are talking about in order for it to work properly. And so I'm going to use this 24 gauge magnet wire and wrap this entire thing with it to create that inductor. Now winding it can be a bit tedious, but be sure to leave a little bit of a length on the end before you start, and then just carefully wind it around, making sure that there's no gaps in between, and make it nice and tight, and also be sure
one of the biggest protests in Australian history, crossing the Sydney Harbour Bridge.